So now we're going to talk about doing calculations with the ideal gas law. So we want to introduce a quantity called a mole, which you've probably seen in chemistry class. It's the number of atoms or molecules such that the mass in grams of the substance is numerically equal to its molecular mass. So 1 mole of carbon dioxide has a mass of 44 grams. So the number of moles, we're going to use this symbol little n. It's equal to the mass in grams divided by the molecular mass in grams per mole. The number of molecules in 1 mole is called Avogadro's number. It's a very large number. Avogadro's number is 6.02 times 10 to the 23. So the number of molecules, if we know the number of moles, little n, the number of molecules in the gas is just going to be little n times Avogadro's number. So if we have 1 mole, we have 1 times Avogadro's number. If we've got 2 moles, we've got 2 times Avogadro's number. So the lowercase n is going to indicate the number of moles. Uppercase is going to indicate how many atoms or molecules there are. So the ideal gas law states that the pressure times the volume is equal to number of moles times the universal gas constant times the temperature, and the temperature must be in Kelvin. Okay, so if you're going to do this calculation, this has to be in Kelvin. So if you're given it in C, you have to convert it to Kelvin first. And pressure, of course, will be in pascals, volume in cubic meters. R is the universal gas constant, 8.315 joules per mole Kelvin. Or equivalently, we can write it in terms of the number of atoms instead of number of moles. PV equals NKT, where K is Boltzmann's constant, which is just, of course, the ideal gas constant, so the universal gas constant divided by Avogadro's number, and it's a very small number, 1.38 times 10 to the minus 23 joules per Kelvin. So let's do a calculation. Okay, and this is one of the main calculations for this chapter. You should be able to do an ideal gas law problem for the test. So on a warm day, 33.3 degrees C, a balloon has a volume of 0.2 cubic meters at 20 psi. If the balloon is cooled to 0 degrees C at 14.7 psi, what's the new volume? All right, so let's again go through and pull out numbers. So I've got T initial is 33.3 degrees C. I've got my volume, V initial, is 0.20 cubic meters. And I've got P initial is 20 psi. And then we're going to go to a temperature of 0 degrees C, a final volume we're trying to find, and the final pressure is 14.7 psi. Okay, so what do we do? Well, we're going to use PV equals nRT. That's the only equation that we have. But we need to make sure everything's in the right units. So my temperature has to be in Kelvin. So I'm going to convert my temperature to Kelvin by adding 273.13, because TC is TK minus 273. TK is TC, the temperature in Celsius, plus 273.15. So the initial temperature is 306.48 Kelvin. The final temperature, let's go ahead and do that. That's just 0 plus 273.15 Kelvin. Okay. Volume, that's already in cubic meters. We're good. The pressure is in psi, so we need to use the conversion factor shown there. That 1.013 times 10 to the 5 pascals is 14.7 psi. So I need to multiply by 1.013 times 10 to the 5 over 14.7, and I get, it's going to be a big number because I'm multiplying by 10 to the 5, 137,931 pascals. And the final pressure well, it's just going to be 1 atmosphere, 1.013 times 10 to the 5, because I'm at 14.7. Okay, so now we've got all our numbers in the right units. Let's think about what we're going to do. So we've got PV equals nRT. In the initial case, I've got P, I've got V, I've got T. I don't have N, and R, of course, is a constant. So I could use the initial conditions to give me N. So let's do that. So N is going to be PV over RT. So 137931 times 0.2 over R, 8.315 times T, 306.48 and I get my N is 10.83 moles. Okay, so now I know everything. What about the final condition? So now finally I've got P, I'm trying to find V, I've got N because I already found that. The number of moles of gas doesn't change. I got R and I've got T. So now I can find my V. So V is going to be nRT over P. So now I can just plug in my numbers. 10.83 moles, 8.315 is R, T is 273.15. Now, if you've done ideal gas law problems in chemistry, you probably use a different value for the ideal or the universal gas constant for R in terms of liters. So remember, if you're going to use the number for R that you used in chemistry, you have to put the volume in liters instead of cubic meters to get the right answer. Okay, and then let's see. Pressure was 1.013 times 10 to the 5. So if I do that, I get my final volume is 0.243 cubic meters. So even though the temperature went down a bit, so you'd expect it to shrink, because the pressure also went down, it's going to expand, and in this case it expanded more than it shrunk. So make sure you're able to do ideal gas law problems. The other topic in this chapter is kinetic theory of gases. So the reason why if you blow up a balloon the walls go out is because there's collisions with the molecules of air in the gas with the walls of the container. And as you heat up the gas, the molecules move faster, and so they bounce off the wall harder, so you can push it out further and the balloon will expand. So the pressure has to be related to the speed of the molecules. So after we do a whole lot of algebra, we find that the pressure has the relationship shown here at the top right. The pressure is 1/3 times N, the number of molecules, times M, the mass of each molecule, the average velocity squared. So the square of the average, the average of the square of the velocity. So the bar means it's the average, and it's the average of V squared. So the average translational kinetic energy, which is just 1/2 mv squared, if I rearrange that and use the ideal gas law, it's just equal to 3/2 times Boltzmann's constant times the temperature. So the average speed of molecules in a gas depends only on the temperature and on the molecular mass. Why is it that we take the average of the square of the velocity? Well, remember, velocity can be positive or negative. So on average, if I look at a gas, on average the velocity of those positive and negative numbers might add up to 0. So I need to square the velocity first, get all positive numbers if I want to get a meaningful average. So the RMS, which is the root mean square, so that means it's the square root of the mean, which means the average of the square. Okay, so RMS just tells me what we did here is equal to the square root of 3kT over m. So if I look in a gas, some of the molecules will be moving really fast, some will be moving really slow, But on average, I'm going to get a distribution that's shown here, where the most probable speed, Vp, is not quite the same as the RMS speed. But as I increase the temperature, what's going to happen is those curves will shift up to higher and higher values of V. So VRMS will increase as the temperature increases. So let's just do a quick calculation. So if I've got 1300 moles of nitrogen N2 gas at 2.1 atmospheres in a volume of 8.5 cubic meters, what's the RMS speed? And they give us that the molar mass of N2 is 28 grams per mole. All right, so what do we know? So again, let's go and gather from the problem. So 1300 moles, symbol for moles is little n, so I've got 1300 moles. 2.1 atmosphere, that's a pressure. And we know we've got to put that pressure in Pascal. So let's do the conversion right away. 1 atmosphere is 1.013 times 10 to the plus 5 pascals. So my pressure is 212,730 pascals. Okay, let's see. Next thing, in a volume of 8.5 meters cubed, that's already in the right units. And we want to know what's the RMS speed. And we're given the molar mass is 28 grams per mole. All right, so RMS speed is 3 kT over m. So I need the temperature in Kelvin. And I also need the mass per atom. Well, mass per atom, mass per molecule, is going to be just the molar mass, m, divided by Avogadro's number, right? So if I know the mass per mole, I divide by how many atoms per mole, or molecules per mole. That should give me how much per molecule. So that's going to be 28 grams divided by 6.02 times 10 to the 23. And I get 4.65 times 10 to the minus 23 grams. I need to put that into kilograms. So divide by 1,000, 4.65 times 10 to the minus 26 kilograms per molecule. All right, what's my T? So T, let's see, I've got P, I've got V, I've got N, I've got R. So T is PV over NR. So P 212,730, V 8.5, 1300 moles, and the gas constant 8.315. And so I get my temperature is 167.3. Okay, so this is a problem where I've sort of pulled in the ideal gas law and the thermal speed at the same time. All right, so I've got T, I've got M. Now I can just plug in that my VRMS is root 3 kT over M. So root of 3. K is Boltzmann's constant, 1.38 times 10 to the minus 23. T, 167.3. And the molar mass is that really small number, not the molar mass, the molecular mass, 4.65 times 10 to the minus 26. And if I do that, I get 386. And let's see, I should round it to 390. And what are the units going to be? Meters per second. So those are moving really, really fast, right? That's faster than the speed of sound in air at room temperature. Okay, so the problem I want you to do is just a simple ideal gas law problem. Again, you're going to have to do some conversions. So I tell you, you've got 3.5 moles of gas in a volume of 2 liters. at minus 150 degrees C. So I want you to first find the pressure, and then if you increase the temperature to 0 degrees C at that same pressure, what will the volume be?